Oh, good. Hey, Michael, hurry up.
Sorry.
Yeah. Hello, good afternoon, everyone. Yeah, good to see everyone again. And we're going to move on, start to talk more about polymer physics today. And as again, we're going to do a previous episode on polymer physics. It's been a while since it's last Thursday. And if everyone remember what it was Lancy class about? If it can boil down to two words, what it will be? Coolant length, chain rigidity, right? That's a parameter we talked about last class is how do you quantify how rigid a polymer is using a parameter to describe it. All the class before that was just talk about end-to-end distance or how big your coil is. And that parameter doesn't have anything to do with how rigid your chain. So walking from what we talked about is, we talked about what would it be there? End-to-end distance in the first several classes. It measures how big these two distances are, right? Then we talk about persistence length or rigidity or how rigid your chain is, right? This somehow is magically matched up with C infinity, which is another parameter we talk about. It's a characteristic ratio. Okay, great. So these two, I talk about both talk about how rigid the chain is, rigidity of the chain, and we all get some idea how they would be affect that, right? And there's one more parameter, like cone length, right? It's basically twice of LP, which is LK. Great. So what else we need to learn for polymer physics class? We now have a parameter that can describe how big the coil roughly is, right? End-to-end distance. We now have a parameter that talks about how rigid it is. Anyone have some creative idea? What other parameter we can talk about? It seems like, okay, done for how we describe a coil, right? I need some creative idea.
Density? Like how dense it is?
How dense it is. Right. Right, that's a very interesting idea. Density, I haven't thought about that. In this case, we kind of assume the monomer is basically the same amount dense. So we didn't take density into account, but in future, that's definitely one of the interesting idea we're going to explore. And we will talk this probably next Tuesday when we talk about the polymer chain in solution. Okay, we can talk about how this different chains being compact or dilute in good solvent and bad solvent. Any help someone can give me? Any thoughts? What other parameter we're going to talk about?
Radius of gyration.
Radius of gyration. Oh, great. Help. So first, I want to talk to you why we need to sort of get one more parameters in this class. It seems these three is good enough to describe most of the chain property. And the first is why we need to study this. Second, I'll talk about how we study this and if anything relate to the parameter we talked about above. And turns out to be there is a very simple relationship, and we will talk about that. So for the first half of the class, I will explain these two to you, why we need to study radius gyration and how. And maybe before that, I'll explain what it is. And through this walk, I walk you through this RG. And for the second half, if we are fast enough, I may talk about the example, sort of example for the homework. Then next week, I will, this Thursday, I'll give you a homework assignment that you can work on details about a polymer chain and how we use these parameters to describe it. First, let's talk about why first, because that's always motivate me to think about why something it should happen or why we need to think about why we study RG. It's a little bit tongue twisting, but since we already have H sort of describe how big your chain, RG is basically another parameter that help you to understand how big your chain is. On the fundamental level, there's no literally any difference between capability of these RG and H. They both describe how big your chain. But there is one fundamental difference is if you look at end-to-end distance, this put a lot of emphasis on what is end segment of your chain is. It describes the end from one chain to another one, right? So it's not a sort of representative. If I would think this class is a polymer chain, let's start from that one on the left side all the way to the right side. So if you only talk about end-to-end distance, we basically only measure the distance between two students. But this class composed about 13 students. We need to give credit to every one of them. So that's why first is we need to consider overall property. Of the chain, right? So this is one of the direct reason you want to consider what's this contribution and what that contribution, not just end-to-end. Second, the more important reason is you will learn in next semester in Dr. Simon's class, end-to-end distance is very hard to measure. If you want to probe them directly, how do you probe these distance? You know, there's maybe some fancy way you can do that. If you can label the end group with some fluorescence dye or other parameters, you can highlight these while not looking at the other chain, then you can measure these distance. But it is very, very challenging and difficult. And you will learn one of the mathematic tricks that allow us to probe how big is actually RG by scattering technique. And Dr. Simon will explain to you why that's the case. How does math works out? Scattering can probe RG. Okay, so these are the most important reason why we actually need to talk about this RG in addition to what we talked about, end-to-end distance, etc. Then what is RG? So today, let's begin the class to talk about what is RG and what's the physical definition. So the name is a little bit tongue twisting as well. Radius of gyration. So what it means by definition is what's the distance, what's the average vector from the mass center of your material. So let me draw a little bit clear picture of this chain. A simpler version. So if you think about the center of the mass, you would probably guess, if you put this on the balance or if you want to put the finger on this plate, the center is roughly here, right? That's the mass center, or where the center of the mass for this particular polymer is. If every segment is weighted similarly, so this is the mass center where you got to cancel out all the weight on different sections. So if we use this definition, we can immediately pick two spots to explain what the mass center is. Why don't we pick two random spots? These two, for example. We call it SI as a vector. Is it too small for you guys to see? It's fine? Okay. Let me actually blow that thing up. So we call it, so this again is the center of mass where your chain is. This is I segment, a random segment. We call it I, and you're going to have a J segment. So these two segments point, which is just the explanation where I and j could be. So we never talked about those type of expression. S, for example, this is Sj, talks about from the vector from the center to a point of your chain. Because previous class we only talked about end-to-end distance or a segment of a chain. Our vector is always on the chain, right? In this case, the vector now, we start from imaginary center of your structure. So by definition, the center of mass basically say, let's call each segment has a little bit weight. Let's call it a. If we add all the masses of each segment and we multiply by this vector, so this will be 0. That makes sense, right? Because that's what the weight center. If you average all the factor out, this is going to be 0 because it's the weight center. Or the vector if you add them up. Straightforward, right? Anyone has any question regarding the definition of the weight center? Or where is the center of the weight? Please.
Are those vectors at right angles?
Hmm?
Are the lines at right angles?
No. I mean, it's a random, so we don't expect this to be. I and j can be anything along this chain. So all I'm saying is, if we define what the center of mass is 0, this would be the definition. If you add all the masses versus the vector, it will be 0.
If you multiplied it by Sj, it would also equal 0?
Yeah.
Okay.
I and j are just any segment along your chain, right? So by now it's going to be sound a little bit tricky, but that's the definition or physical definition of end-to-end distance. The radius of gyration. So radius of gyration is basically defined as the average of all these vectors distant to its center and average out. You can see some of them will be a little bit longer, some of them will be a little bit shorter. But if you average out, that would be the definition of radius of gyration. Any question? So let me write this thing out. So Rg basically will be equals to half, or basically average of these S. If you recall, we also long time ago defined end-to-end distance h would be any vector along right? So they are sort of defined similarly, but end-to-end distance is basically, let me put on h average, the end-to-end distance average. But now radius gyration is basically this distance average. So some of them are longer, some of them are closer. If you average out, this will be what do you radius of gyration. And you immediately call it this Rg will be smaller than the overall of the chain. And don't be confused with it, because Rg is likely to be a value that's smaller and condensed than the overall space you're going to occupy by your chain. Okay? All right. Now, the question is, how can we understand how big this is the radius of gyration? And is there any connections for this physical measurable value, which by light scattering or X-ray scattering or any scattering type of technique can measure this Rg, okay? And is it linked to end-to-end distance? That's the first part of the lecture, is how big is Rg. I won't bore you too much, so let me first do a little bit direct message, unlike the last class. So the Rg we will learn will be or this value will be 1/6 times of what you would have for the end-to-end distance. √6. I know I'm missing some. Wait. Okay, so or this will be h squared. So it's a factor of 6 times smaller. If your end-to-end distance on average is a value, then RG is the value divided by a √6. So in the end, it's a happy ending story, because if you measure RG, if you do a light scattering, you make a polymer, you dissolve it, you do light scattering, you get the RG. Let's say arbitrary number is 20 nanometer, okay? Then you know what the end-to-end distance is. You just multiply by √6. What you're going to get is the end-to-end distance. And if you know degree of polarization, then all the rest is easy. You can calculate characteristic ratio, chain rigidity, etc. So that's the whole reason why we actually measure RG. So before I move on, I want to make sure everyone understands the most important point of this class is why we define a value, why we define what RG is, and how does RG relate to the parameters we measured previously or discussed previously. So any question regarding the lecture up to this point? Fairly straightforward, huh? Okay, so what we now, the next 30 minutes, I will do something again, because it's a polymer physics class. I will explain to you a little bit how we get this very simple relationship between RG and h squared. It's actually not that too bad. It's relatively simple. So everyone has studied the math in their high school, and a very famous triangle relationship is, if you know the. So again, I drawn this SI, SJ, and this one, if we a diagonal of this two segment, and we define that's basically Rij, right? Rij. So that should be I is here. This is a J. So that's basically a triangle relationship. If we somehow can convert the mass between the SI, SJ, etc., convert to R, Ij, then this can be linked to end-to-end distance, h. So I'll first explain the logic what we are doing here. Because this is linked to Rg. Rg is everything from the center of the mass of your chain to onto your chain, right? Logic, okay, first. Then, through this very interesting triangle relationship, where we can use the vector Si, Sj, and convert these two, Si, Sj, to Rij. Rij is now, all the vector is on the chain now. And if you recall the first several class, the vector R and the J, they can be converted to end-to-end distance. So what we're going to do is now play a little bit deeper in the math, how we can use this relationship to link these two parameters. Fairly straightforward, right? So first, we're now going to go back to this relationship. How does these Si, Sj, and Rij can be linked to each other? Triangle. So let's call this will be theta. Let me first write the equation, see if you're going to be familiar with that. Or let me read. Let's call it A, B, C. This is theta. C squared will be equals to A squared plus B squared plus 2AB this you have to know before we go on to explain how we can use radius or gyration to explain how you can connect these two parameters, right? Any question for this part? How we can use this triangle relationship to obtain the knowledge we discussed here? Any question? So this is the easy one for us to understand. Now, why bother with this? Why we bother, converting these two again is I now can link this to H and link this to RG and get a value about how these two will be connected. Okay. Is it too much equation or mathematics? I see. Huh?
Not yet.
Not yet. Okay, right? I just started explaining the concept first, how we can link all these everything together, right? So, again, whenever we talk about mathematics, I feel it's my responsibility to explain to you. We want to test it in the final exam, so I just want you to follow with me once in the classroom, how I can explain clearly how each parameter are linked and connected, so that when you go back to read the textbooks, you won't have trouble to understand the equation they showed them. Okay, so now this fancy equation. So we're gonna do some of the very simple math first to sort of connect them. To connect all the dots. So where we should start is first we now consider the vector Si and Sj. So Si dot Sj is basically these two vectors, I and j. We're going to do a dot operation, and we know this will be Si, right? It will be Sj. This is by definition, so we don't have any fancy operation yet. A, B vector use a dot pattern equals to A dot B dot cosine angle between them. Now, so if we use the equation above, this value is the same as here, right? So, right, except the 2 exactly. So you can basically use R ij minus Si minus Sj squared divided by half divided by 2 will be equal to this. all we did is just move these two to the left and divide by a factor of 2 in the front. Pretty clear what we are doing there, right? So there's one more step, then we can reach our answers. Oh, where is the eraser? I cannot function without eraser. Oh, here you go. And by the way, we also need to define this thing. This is the definition of RG, or radius of gyration, equals to s squared, right? And divide by a half. So, now, if you consider average of all these parameters, an average of SI dot average of SJ, we give it a bracket, consider all the average of this, and we know by all the average direction, if we add every consideration, all the possibility of the chain, because we cannot take one just one I, one J. We're now going to consider every possibility along this segment, right? So we need to add up everything and take an average. And I won't rewrite everything on the left, but this parameter, this will be equals to 0. Because SI and SJ, if they consider average all of them, it will equals to J equals 1 to n. Right? So this, what we basically describe, this will be equal to 0. Because all the SI and SJ, if you dot and average them, there's no value going to be left. And you will be amazed what we can do now if we know the average of all these values will be equal to 0. We now can rewrite the equation on the right hand. So if this is a 0, right? SI/SJ is 0. Now, this is basically going to be equal to 0. Now we can directly link what will be Rij and SI/SJ are. The reason we want to link them again, this is a plot or the game plan we talked about at the beginning. If we can link these two, now we can talk about RG and H. Anyone have any question up to this point? All right, if not, then let's talk about this. So, how about this parameter? So if we add everything for the SI, I equals n 1 to n. This is the basically definition of RG, or part of the definition of RG, right? So you will because this will be RG, and wait, there's not divided by 2, so it's basically n squared multiplied by RG squared, because RG squared is basically equal to this, or average of s squared. So if you look at here, this equation basically says now if we add 1 to n, j 1 to n, so this comes down to this n squared term, and this term is basically RG squared. And if we do it again for Sj, it will be the same, right? Sj id 1 to n, if we take an average of it, j equals 1 to n Sj these two will be the exactly same. A question in the back?
What is n?
N is basically the number or the segment of your chain. Well, in your chain, you're going to have 1, 2, 3, all the way to n segment. So when we consider the radius gyration is basically, this is definition by one segment. But if you want to consider the whole chain, you need to take an average of all the segments, or SI, right? So let me write it here. SI is from the center of the mass to there. And now if you look at the equation here, we now know what is this term is. This will be basically SI. If we consider add everything, this is basically RG squared. This is again RG squared. This will be 0. And how about Rij? Rij. What would be Rij equals to? That's a tough one. Rij. So what does Rij mean first? Rij is basically a vector from a segment of I to segment j. So if we come back to here, so this would be the chain. Rij is, this is segment I. I could be any part of the chain, right? J could be any part of the chain. So Rij is this vector from I to j. If I equals to 1, and j equals to the last of the chain, Rij is end-to-end distance, right? If R and J is just one number apart, it's basically tell you Ij equals to the bond next to each one. Is it clear what is this fancy Rij is, and how does it differ with h squared or h or end-to-end distance? So it's basically tell you that would be the bond along the chain, any bond, the vector along the chain. Okay, so if we use this term, Rij divided by Rij, it will tell you
NL squared.
very good, close, very close, and very close, almost there. NL squared. N is basically the segment, right? since we now A and B, I and J are random, so this will not be N. It will be I minus J, because if I and J are next to each other, this will be 1, right? Or if we have a special case, I and J are first and the last segment, so this will become N, correct? And this will not be L squared. This will be B squared. And anyone recall what this B is? B is effective.
L squared times C infinity?
Yeah, so B is equivalent segment length. So we talk about H squared equals to C infinity and L squared. This would be characteristic ratio number of bond and L. Or this will be equals to N B squared. This we call it effectively free joint chain model, right? So these are basic say. So in other words, what we now doing in this way is we now sort of converted any distance between two bonds to this MB square or C infinity MB square. And it will be very useful, you will see. And I like you give me a very easy answer to continue. And so what we write here is Ri Rj. This would be basically any I and j. It will be equals to I minus j, or distance between each bond, right? If I is equals to 1, j equals to n, which means this is the first bond, that's the last bond, this equation will be a special case will be mb squared, right? That's basically end-to-end distance. Okay. I feel we are so close now. We have a way we can calculate what is r dot to the r, or r squared is. So we know what this is, right? We just write it there. We know this will be the rg squared. This will be again rg squared. This will be 0. Now we can basically get what is rg squared is. Agree? So this term is 0. This is rg. This is somehow relate to what's the distance between each chain segment. So there is a second definition of what rg is. So second definition of what Rg is basically is average of all the possible segment average. So this was coming from the equation right here, from this. Any question for this? How we get this definition about Rg squared? And any question about what's the physical meaning about this equation? Please ask a question. Yes?
Rg squared is just the radius of gyration in both the I and j directions all summed up.
Right.
According to that. Okay, cool.
Yeah.
That's
So the first definition is more easier to understand. There's two ways you can define what RG is. The first definition is what the vector to the center of it, or average. So the center of mass, we can call it a star. So, and this is the imaginary point along chain, right? And this is your physical chain, like a winding mountain road. So this, from the center to each point of that, you can draw a vector. And by definition, by first the definition of what RG is, radius of gyration would be average of each individual factor. So this definition relies on what the center is. If once you know the center of the mass, you can easily draw what is center of the mass to the chain, vector 1, Si, S2, all the way to Sn, right? So you're going to have a lot of these vectors, and you take average of every vector. You got the first definition of what RG is. And we just talk about second definition of RG is right here. In this definition, it does not require we know where the center of mass is. So this point, we don't care anymore. But what we care is we now know what would be each individual bond distance. Rij is basically, let me give you an explanation. Let's first fix I equals to 1. Okay, so I going to be always 1. J will be equals to 1 to n, right? I equals to 1. Well, now we can add all the j component. So what does this mean? Physically, or real world, not just mathematics. So that means we're going to average out all the R, 1, 1, 1, 2, all the way to 1n. So 1, 1 is basically a bond next to each other, right? Vector 1, 1 is segment 1 to 2. So what we're going to do is now pick 1 as starting point. Now draw all the vector along the chain and do average it. Right? So now we can start I equals to 2. J again do the same trick. So which means we now going to consider 2 as vector. So second definition of what this RG is basically all the possible vector you draw every 2 point in your chain and average them out. This is not as direct as the first one, but it also works out in this way. What does again physical meaning is every possible point between 2 points on your chain, and we're going to take them out and average out. This will be the end-to-end distance. The RG, not end-to-end distance. And if you look at where I written at the beginning of class, why we cares about RG is now you see the definition. RG is equals to Rij. I and j could be anything along the chain. While h squared is basically a special case that looks R and J. I would be equals to 1 and J would be equals to last one. That's basically the definition of what this thing is, right? Because this one is sort of communism. Everyone has play a role, and we're going to average of every single point along your chain. Well, the end-to-end distance is only consider 2 of the heroes in the community is where the first and last bond. Okay, so if we know this, the rest is relatively straightforward for us to figure out. Because Rij is very easy to calculate. Rij is, we discussed it here. Rij would be this value. I equals to 1 to j and b squared. Right? So let's give it a little bit of kick, finish this definition, then we can go to a few examples. Okay? We know this equation. We know Rij, any possible vector equals to, on your chain, well, equals to this is basically a distance of between bond and B square, right? Ij is just the distance between the bond I and bond J, right? So any distance between these two is going to be can be calculated by end-to-end distance. You can consider if you chop everything away, it's basically end-to-end distance for this smaller segment. It's going to count what is distance from I to J, right? So J minus I will tell you how many segments there, and B square. Okay, so now next is more fun. Is now we're gonna play a kindergarten game on this chain with n bonds. Okay, 1 to n. How many of them has a neighbor? Let's say for cases where I and J J equals to I plus 1. So which means I and J are neighbor. They are the bond next to each other, right? So next to each other. Or basically a segment that is next to each other. How many of them?
N minus 1.
M minus 1, right? You're going to get M minus 1 possibility for I J equals to I plus 1, right? That's how many possibilities. Because you're going to take one as a direct neighbor, then you can count how many of them. Now, how many possibility of two neighbors apart?
N minus 2.
So that you can do, so J equals to plus 2. That means it's going to be neighbor, neighbor. It will be M minus 2 possibility, right? So you will quickly see if you sum everything of the top up, you can simplify what the value of that. And if we consider J equals to I plus N, N is the whole length, then there's going to be only one configuration, right? If you take the whole chain into it, there's only one possibility. You can count every bond there. Right, so this is one possibility. Okay, so let's do now summarize this. How we can simplify this mass. So if we write this. Coming back to this equation, we now can simplify this term, Rij squared to be end-to-end distance, right? So we're still going to have 2n squared. This is this factor. Rg squared still going to be equal to that. And it will still have, but now this is I minus J B squared, right? So this is a constant. So we can directly move B squared to here, outside this sum function. So in the end, it's simplified to a mass that as long as we can solve this, we are all set. as long as we can resolve this equation, we're all good, right? So we're going to take a break, then we come back to this. But we're very close to what we're going to get in terms of what the end-to-end distance, okay? Let's take a 5 minutes break, then we can wrap this up and talk about a few examples.
Can I ask you?
Yeah.
So is this all these equations plus the radius of gyration? Is this pretty much everything we need to solve for any of these variables?
Right,
Is there anything
right.
I'm missing?
No,
We can.
no.
Seems
That's
pretty-
basically, yeah, this is pretty straightforward in terms. If you go back to watch what we talked about first 20, 30 minutes of the lecture, which explains why we need RG and how does it relate to end distance, you will understand the bigger picture. I mean, the later 30 minutes of the lecture was for me to explain how they would be mathematically linked together, right? Because that's something we need to discuss briefly throughout the class. Mm-hmm. Excuse me?
Are there 3 different overall equations for radius of gyration, or are we still just deriving our one?
So,
equation?
so there's basically 2 definitions of what the radius gyration. One is defined by the classical way of center of mass, and how does the radius gyration relate to the center of mass. The second is a variation of what is radius gyration. Is basically you don't need to consider center of mass. All you need to consider is all the vector along the bond. So you basically average all the possible bond on one chain. Michael, what happened?
I don't know. Must be raining paper.
Yeah. All right. So. So let's first ask you guys. I want to recap the essence of this class. It's why we need to find radius of gyration, and how does the radius gyration link to what we talked about in the previous several classes. And a lot of you might, that's a key for you to take home message is why we need radius gyration, because it's something measurable. And I wouldn't be able to teach this class because of that's more like Professor Young Simon's class. You will learn more details why we can measure it by scattering. And again, if you look back, what we want to do is to explain why RG is linked to end-to-end distance and how they mathematically relate to each other. And in the end, it's a very simple equation I explained to you at the beginning of class. RG squared is just a end-to-end distance divided by 6. And so the rest of the class, last 30 minutes, I'm trying to explain to you why their maths have magically work out. Okay, so we're very close to the eureka moment, or why that's the relationship between them and why everything works out. And if we look back what we talk about in the class, we try to use a triangle relationship to work it out, because all the end-to-end distance only relate to the vector along the bond. Any end-to-end distance value relate to all the vector along the bond. It's sort of relate to that Rij, right? So bond I and J. So that is what Rij is, and that's related to end-to-end distance. End-to-end distance is special case of Rij when I equals to 1, J equals to n. That's basically end-to-end distance. And we use the triangle relationship to understand, because Si, Sj, and Rij can be linked. And in the beginning of class, we talked about how does Rij and can be related to each other. So at the end of the triangle relationship, we basically found Rg can be defined by a second way to talk about that. Rg can be basically defined by this equation, which talks about how does Rg relate to Rij. Through that fancy triangle relationship, we know a second way of definition of what is Rij. Rij is average all the bound possibility between the segment I and J. So in other words, Rg will be directly related to end-to-end distance, but we haven't figured out why. So the rest of the class, we're going to figure out how does Rij can be linked to end-to-end distance. And we talk about Rij, this Rij. So a special case of Rij, it can be think about as end-to-end distance. If we sort of, maybe this is easier to do it here. So Rij is basically any bond between I and J. So if I and J are neighbors, that means it's a bond next to each other. If I and J is kind of far away, it can be this, I is here, J is there. If I equals to 1, J equals to n, then this will be the end-to-end distance. So something that we can cheat about Rij is, what if we chop away the rest of the chain? You can see Rij is now become just end-to-end distance, right? So this Rij will be equals to nb squared. And number of segment n is basically I minus j, or the distance between these two. Right? So that brings us to here, where we now, if we plug in on ij is equals to this distance I minus j b squared, this will be relationship, and now b is a constant, right? B is a segment length. It doesn't depend on this I and j, so we can basically say, hey, it's not comfortable, stay inside this bracket, let's move you out. So we can move the b squared to here, outside the box. Then the rest of the equation or mass what we need to solve is just this sort of a little bit complicated but solvable. What is this equation equals to? And I will take the first 10 minutes to walk together with you to solve this equation, and we will get the final moment with the RG and how they relate to end-to-end distance. Right? So this, coming back to this topic, or I have helped you put it here. How do we understand this equation?
If you do your matrix, it would
Yeah.
be half of the whole matrix, which the matrix should be equal to
Right,
squared, the end-to-end distance.
right.
Should be the end-to-end distance divided by 2.
Roughly close. Yeah. It's a very good way to think about, because what we talk about is the matrix way to think about the problem. What he specifically mean by the matrix is now, we already did a little bit here. So if I equals to j is next to each other, you have n minus 1 possibility. And if this is a 2 bond away, you get n minus 2 bond possibility, right? If you are n bond away, there's only 1 possibility. So this basically can be summarized or converted to this equation from top to bottom. Okay? And why is that? So let's think about, we're going to call it a new constant k. If k equals to 1, what you have is 2 multiplied by k multiply n minus k. So what does this mean is there is n minus 1 possibility. So if you look at here, there's a minus 1 possibility if for them to neighbor. So in other words, if we draw a matrix, we're gonna again draw it diagonally. So if they're a neighbor, there's a n minus 1 possibility. So it will be 1, 2, 3, 4. It will be n minus 1 possibility if j equals to I plus 1, right? If the j equals to I plus 2, you're going to lose 1 possibility. So what you're going to have is just a 1, 2, 3, 4, and minus 2 possibility. And you can continue to do this. M minus 3 possibility. So if you write all the metrics out, it's basically, again, a half of the matrix, right? So in the first row, you got n minus 1 term. Second row, you get total of n minus 2. Now you just need to add everything together. It turns out to be this. So let's take a look at this equation. 2k multiplied by this. So if k equals to 1, it's basically everything is equals to n minus 1, right? Does this make sense to you guys? Are you sure? Everyone is sure? Good. So this describes this matrix. k equals 2. And we can do several tricks to see. So if k equals to 1, this will be 1, and you will add all the n minus 1 term, right? This is the total number n minus 1. If k equals to 2, there will be 2 multiplied by n minus 2. Right? Because it will become less possibility. So, in this equation, since 2 is a constant, k is a variable, n is a constant. So you can break it down into 2 parts. So now the math is relatively easy, because now we only get one constant. We're going to, by 2k multiplied by n, so we can take the 2, and n is a constant, so n is a constant, so it will be 2k. So k, sorry, not 2k, right? So that's the first part, and we get a second part, which will be minus 2, k equals to 1, and minus 1, k squared. Okay, this again, this part is relatively mathematically simple. We basically need to sum up all the k. K will be equals to 1 to n. While I was in the elementary school, our teacher showed us a story how you can do this. There's 2 students in the class while they add all the numbers together. The teacher asked them, can you add 1 to 10? And everyone can do that. How about 1 add to 100? This is the same. Sum of all the k from 1 to n minus 1 will be equals to, let me find some of space here. K equals to 1. So this is basically means we need to add 1 plus 2 plus 3 plus all n minus 1. And you know how this would equals to, right? You're going to equals to, first term is 1 plus the last term is n minus 1 multiplied by a total number. You go, total number is, you got n minus 1. Is this clear to you guys? How we can get this? Good old calculus, yes. If we need to count 1 plus all the way to n minus 1, this is a shortcut. You can understand that. The total number of them is n minus 1, from 1 to n minus 1, right? And the first is 1, last n minus 1. You take the average and multiply how many of them. Okay? All right, we are fairly close. There's a second term we need to resolve. Is this. It's a little bit tricky, but similarly, we can get this. Now, this is basically, you say, I'm going to add 1 square, 2 square, 3 square, add up all the way to n minus 1 square. And again, it's a calculus problem that you can simplify this by, as the equation as here. So, let me make sure I give you the right answer. So this will be n Yes, that's you can do the simple, again, the mathematic transformation of this. So now a little bit back and forth, but if you look at this these two terms, as long as we can use first term minus second term, we get what is Rg equals to what will be the mb squared, right? So use the first term minus second term, we will be able to get the Rg, what the Rg value is. So let me help you for this minus this. The first part is 2 let me do this. And we know what the value that it would be, n m minus 1. And the second term okay. This we can fairly easy to resolve, right? Now there's no such thing as sum everything up. This is now become elementary level mathematics. So let's figure this thing out. So we can write as n multiplied by n, m minus 1. Again, this will be the same as first term.
Where's the 3 coming from?
3 is coming from the 1.5. If you 3 divided by 6 will be half the same, because we're going to start to merge this first part with second part, where you're going to minus again n m minus 1. Let's do some tricks. So what they are in common is these. They both has these two terms. But what this is not there is basically what we care. So n will multiply this basically is what we written here. Then you will have 3n minus 2m minus 1. So if you see what this is basically tell you, this bracket is 6 divided by n plus 1. Right? This large bracket. Make sense? So now if you multiply this term, m squared b squared, and basically we can cancel out this n versus this two term. What you will left is 6 divided by n squared minus 1. And this when n is a large chain, if n is very large, the second term, b squared divided by 6n, will be much smaller than what has been left on the left, right? So you basically simplify this equation to voila, that's what we talked about at the beginning. So a little bit long and winding road, but it's a happy ending that you know how does these mb square and linked to rg square. And we actually take one approximation is we eliminated this minus b squared divided by 6n term. And if you don't have this term, then rg can be directly linked to end-to-end distance. Okay? That's where all the mass is coming from. And I hope I explained what's the rationale we start off to use that fancy triangle relationship and how we counted everything together to link these two. For the rest of the a few minutes, let me re-emphasize that how we can measure RG, and in reality, what you would be doing versus RG in a real experiment. So let's say you synthesize the polymer. You basically don't know what n is. Unless you do molecular weight measurement, you can use that to divide by what the value would be in terms of n segment. If you measure molecular weight, you know what it is. And you know the monomer molecular weight, you can divide that out to get what is the molecular weight or n, or degree of polymerization n. And what you can do in terms of scattering is now you can measure what is RG is. So what typically do is people would do this type of measurement. So where they can plot RG squared versus n, and they can actually get information out. And they can get these two informations. Right? This is a measurable. This is a measurable. Or at least this is molecular weight is measurable, right? You can measure the molecular weight. You can measure the RG. This is by light scattering. This is by GPC. So you can sort of get a relationship between what are these two are. And a lot of time you will get a relationship between them. For example, I won't go in too deep, but let's say, what if you get RG can be plotted as 0.25 molecular weight and power of 0.51. I mean, this is possible, right? You can plot them and you can get what the slope is and what are these values. So if you can get this type of a relationship, you can directly get what is persistence length, characteristic ratio, and you can know a lot about chain conformation for your sample. In next class, we will talk about a few real-world examples, how you can measure these two, and I'll show you a few examples how we can measure the RG, measure the molecular weight, and calculate what is LP, C infinity, and we will follow up with some homeworks next week, next lecture, to show you how you can really use what we learned in the first few lectures to help you understand your polymer is rigid or soft or semi-flexible or it's a non-linear fit. That means the polymer is not synthesized good. Okay. So any question for this class where we talked about how there's two definitions of RG and how does RG is linked to end-to-end distance and why we need to learn radius gyration. If not, then we can summarize today's lecture, and for the next class, we'll start with some example and discuss more. Okay?
Can you measure with Sax wax?
Yes.
Demo?
Yes, we can.
Really?
I mean, this is basically a part of the class you would learn in the techniques class, right? But
Teach techniques.
but in terms of scattering, it doesn't matter if you use a light or X-ray. They do the same thing.
Today? Yeah. That's weird that they would be.
I like teach the techniques about scattering part because that's relatively straightforward.
I was driving in and I saw.
I don't know if Dr. Patton's gonna go over
Yeah, maybe
the sex
I
wax.
love that shirt.
you're not too busy. I'm sure you've heard this semester.
I didn't like that it takes time.
I need a tank top.
Oh, I'm sorry.
The labs, I'm not sure 100%.
With the